So okay, in the next class we have discussed about some programs. So in this class I will discuss some more programs. So the next program is conversion of Fahrenheit into centigrade. For that you have to write the program. So we know that the conversion formula is centigrade is equal to F minus 32 into 5 by 9. So given F value, you have to find out C. For that you have to write the assembly language program using 8086. So you assume the appropriate locations. So in data segment, let the starting of this one is 50,000 H and with the offset of 5,000 H, the value of Fahrenheit is stored. And they store the result centigrade in location with a offset of 6,000 H. Okay. So the program will be, the first two instructions are move AX comma 5000, move DS comma AX. Then you take this Fahrenheit value which is stored in 55,000 location onto AL register. So you have to find this offset with some register, say SI comma 5000 H. Here one of the advantage of assuming these locations is, instead of this move SI comma 5000, you can also write move SI comma AX also, because the data segment register also points to 5000 H and the offset is also 5000 H. So in this particular example both are matching, so you can directly take this AX contents onto SI. This will save 1 byte. Okay. So I am taking this into AL, move AL comma contents of SI. Now AL contains the Fahrenheit value. So you have to subtract this 32 from Fahrenheit value. Okay. So in order to subtract this, before subtraction of this one, you have to perform the division also later. This is division. So we have division instruction directly, but the division instruction will be for 16 bit by 8 bit and 32 bit by 16 bit. But here this Fahrenheit value is only 8 bit only. Okay. So the numerator should be 16 bit. Denominator can be 8 bit. So before subtracting the 32 and performing the subtraction, what I will do is I will convert byte into word. This is sign extension. Now AL will be having word. AL, the sign bit of AL will be copied onto AH and this becomes AX. AX will contain now F value. This I have explained in the instruction set. Convert byte into word. Okay. Simply the sign bit of AL will be copied onto AH. Now the question is, so why you are taking the sign bit? Here because the Fahrenheit can be a negative value also. That is why you have to use the sign numbers. Here we are assuming that F and C are sign numbers. So in case of signed multiplication or signed division, so you have to extend the sign if you want to perform 16 bit by 8 bit division. So this is CBW. Now AX will be having Fahrenheit value 16 bit equivalent of this 8 bit value. Then you have to subtract 32. You take some CL or something 32H. The problem is here 32 is decimal. Okay. but you have to subtract hexadecimal value. So this will not be 32. What is the hexadecimal equivalent of 32? Because the microprocessor will perform the hexadecimal operations, but this 32 is decimal value. Okay. So 32 decimal is equivalent to, what is hexadecimal? 16 2s are 16 2s are 0 is the remainder, 16 zeros, 2 is the remainder, 20h. So you have to take 20h here. This is one of the important point here. Then you have to multiply with 5. So you take move. 5 is actually this whether this is hexadecimal or decimal, both are same. Similarly 9, subtract ax comma sub ax comma, you can take cx because the source is 16 bit, you can take 0020h, 0020h, then subtract ax comma cx. Now in ax what will be there? A 16 bit equivalent of f minus 32. Okay. Now this we have to multiply with 5. So you can multiply either 16 bit by 16 bit number or 8 bit by 8 bit number. So you take this 5, move 5, anyhow this is positive number, there is no need of sign extension. I will take this directly into some register, say bx comma 0005h. I will perform mul, I mul, because numbers are signed numbers, I mul ax. So what is the operation here? Ax and bx will be multiplied, and the result is stored in dx ax. Okay. Now in dx ax we will be having 32 bit result of this 16 bit into 5. Okay. Now you have to divide this with 9. 9 also you have to take 16 bit data. So you take move bx comma 0009h. You may get some remainder also. So I am going to neglect the remainder. So I am taking only integer value of this. I am not considering the fractional part. So then I div, this is 32 bit number and this is 16 bit number, I div bx. So this will perform dx ax by bx. This dx ax was f minus 32 into this one, dx ax will be having 32 bit equivalent of f minus 32 into 5, that I am going to divide with bx. Bx is having 9 now. So after this I division, the remainder will be there in dx, that I am not interested, and quotient is there in ax, that I am going to store into this location. For that I am writing move si or bx, any value si you can take, si comma 6000 h, move. So this remainder we are going to neglect, quotient will be there in ax. Okay. So that I am going to store in si. This is the program which converts the Fahrenheit temperature into centigrade temperature, which is a direct formula computation. So we will discuss the next program will be, suppose if I want to compute in cx register, I want to store say 5 into al contents minus some 6 into bh contents plus contents of bh by 8. Basically this is multiplication. Okay. So we will be given al value, bh value, we have the registers inside the 8086 is bh. So you take those values, you multiply al with 5 multiply BH with 6 and divide BH with 8. So, you add this to 5AL, subtract 6BH and you store that result in CX. Okay. Here no need to assume any locations because already AL data, BH data is available in the microprocessor. Okay. So, I am assuming the same data segment contains with 5000H, move AX comma 5000, move DS comma AX. Then you compute this step by step. Okay. 5 into AL. Okay. So, you have to take 5 into some register, say move BL comma 05H. Then let us assume that these numbers are unsigned numbers. Mul BL. AL is already there. Okay. So, in mul BL what happens? Mul BL is 8 bit by 8 bit multiplication. In case of 8 bit by 8 bit multiplication, as we have discussed, one of the operand will be in AL, second operand can be either register or memory. Here I have taken register BL. The result is stored in AX. This is the 8 bit by 8 bit multiplication. So, I have taken this 5 into BL, AL already some data is there, I have multiplied with BL. Now, in AX this 5 into AL will be there. So, after this in AX 5 AL will be there. I am taking this into some register CX. AX. So, in CX also I am storing same 5AL value. Why? Because I want to use this AX in the other operations also. Okay. Because in multiplications and divisions, this AL and AX will be used by default. That is why I want to store this temporary value, intermediate value 5AL into some register CX. Okay. Now, we have to perform BH into 6. So, for that you take 6, move AL comma 06H, or you can directly take AX because you have to multiply, only AL is enough, sorry, AL comma 06H, then mul BH. So, what will be the operation here? This will be contents of AL into contents of BH. So, contents of BH as it is, whatever the data available in BH, that will be taken, and contents of AL is 6. So, this will store the result in AX. So, after this what will be the contents of AX here after this operation is 6 into BH. 5 AL is present in CX register and 6 into BH is present in AX register. Now, you have to subtract one from the other. Okay. For that you have to subtract this 6 BH which is there in AX has to be subtracted from CX comma AX. So, here CX contains now 5 into AL minus 6 into BH. Okay. Then you have to perform BH by 8. Okay. So, this division by 8, division by any power of 2 can be performed by using simply shift, no need of using the division operation. Okay. So, here this is basically how to shift by 3 bits to the right or left, to the right. Okay. For example, if I take say for example 100 is 4, if I shift this to the right by 1 bit position, what happens? This is 0 1 0 which is 2, this is equal to 4 by 2. If I shift one more bit 0 0 1, this is 1 which is 4 by 4. Okay. So, given a number, if I shift to the right by 1 bit position, then you are getting half of that value or divide by 2. If I shift by one more, you will get divide by another 2 which is total 4. So, if I take 4 bit number, for example 1000 which is equal to 8. If I shift to the right by 1 bit position, this will be 0100 which is 4, one more bit position 2, one more bit 1. Okay. So, after 3 shifts, this value became 1 which is equal to 8 by 8 which is equal to 1. So, this is division by 8 can be performed by just shifting to the right by 3 bit position. So, in order to shift by 3 bit position, you have to add zeros here, this is important. Okay. So, in that case you can use move CL comma 03H, the number of bits to be shifted. If it is a single bit shift, I can specify in the instruction itself, whereas if you want to shift by more than 1 bits, you have to take into CL by default, as I have discussed in the instruction set. Then you have to shift which bits has to be shifted, BH contents, SH or shift right BH comma CL. So, this operation will shift the contents of the BH by CL number of times. CL we have 3. So, after this what happens is, and the result is stored in BH only. So, BH by 8 will be performed here. Okay. This we have to be add this to the previous value. Okay. Then add, where is that remaining result, CX. So, because this is unsigned numbers, I will take move BL comma 00, so that this also will become 16 bit number. Then add with CX comma BX, then alt. What will be there in CX? The previous value of the CX is 5AL minus 6BH. Now the value is BH minus 8. So, this value will be, the 5 CX contains now 5AL minus 6BH plus BH by 8. So, this is how we can write the program. Okay. So, this basically involves multiplications and divisions, but division we are not going to perform using division instruction, because this is a power of 2, we are going to implement by using shift operation. This is program to compute this. The next program is conversion of the binary into gray. Convert 8 bit binary number into gray number. Now, to write the program for this conversion. Okay. Let us assume appropriate memory locations. Say in 55,000 H, binary number is there, 8 bit binary number, and is stored in 56,000 H, the corresponding gray number. Starting is 50,000 H, ending is 5FFH. Okay. Now, how to convert the binary number into gray number? So, what is the general procedure? If binary number is, this is B7, B6, B5, B4, B3, B2, B1, B0. Gray number is G7, G6, G5, G4, G3, G2, G1, G0. So we know that you might have studied in your digital logic, G7 is equal to B7 and G6 can be obtained by exclusioring B7 and B6. Similarly, G5 is exclusive between B6 and B5 and so on. B5 and B4, G3 is B4, B3, G2 is B3, B2, G1 is B2, B1, G0 is B1, B0. So you have to keep in a loop and you have to do 8 times the exclusive operation. Instead of that, the logic that we are going to use here is, but by somehow if I shift this given binary number to the right by 1 bit position, okay, so that this B0 will comes into this MSB position. So B, if I want to shift by right 1 bit position, so what will be the result? There is one instruction where this MSB will be loaded with 0 if I reset the carry flag. So this bit becomes 0 if the carry flag is reset. Then B7, B6, B5, B4, B3, B2, B1. So B0 will enter into the carry flag will comes onto the MSB. So this will be after shifted version. Okay. This number, if I exclusive OR with G, then what will be this result? B itself. You call this one as shifted version as this is equal to some B shifted version. Now here I will write here B is B7, B6, B5, B4, B3, B2, B1, B0 and B shift is equal to 0, B7, B6, B5, B4, B3, B2, B1. If I perform the exclusive OR operation between B and shifted version of the B, 1 bit shifted version of the B, what will be result? 0 if I exclusive OR with B7. So what will be this? B7 itself, because 0 if you exclusive OR with B7, you see nothing but 0 into B7 bar plus 0 bar into B7, which is equal to B7 itself. So this will be B7 itself. So what will be this bit? B6 exclusive OR B7. This B7 itself is G7. You can also call this one as B7 or even G7 also. Both are same. Then what is the exclusive OR between B6 and B7? Which is G6. And this is G5. This is G4, G3, G2, G1, G0. So you will get the result. The basic logic here will be, you take the given binary number, you rotate right by 1 bit position through carry. Before that you have to clear the carry. Then you exclude OR the given number and shifted version. You will get the gray result. Okay. The program will be, so the first two instructions are same, move AX comma 5000, move DS comma AX. Even you can call move SI comma AX also, because here offset as well as data segment are same. You have assume the location such that both are same. So, instead of move the address, we can just directly transfer the AX content to SA also. Then CLC, this is important, carry flag I am going to reset. Okay. Then you take this onto AL, because so I want to rotate these contents, move AL comma contents of SI. So that in AL, after this AL contains the given 8-bit binary number. This we have to rotate to the right by 1 bit position. R C L AL comma 01. So that what happens is this 8 bits this is A7, A6, so on up to A1, A0, and here carry flag will be there. So this will rotate here, this will go here, this will go here, this will go here, this will go to carry, and carry will go to this one. So as a result of that, what happens is whatever the carry flag status will come to the MSB bit. Okay, because here I have cleared the carry. So after this RCL operation, AL, before this AL contains 8-bit number, after this AL contains zero. So in the previous example, 0 comma B7 to B1, B6, so on up to B1. This is shifted version. Then you have to just do the exclusive operation between these two. Okay. So this you can take this AL into, you store here, because if I rotate this, the previous AL contents will be lost. So you can move these contents onto some BL register. So that BL will contains the original 8-bit register, 8-bit binary number, AL will contain shifted version of this. Then exclusive OR between AL comma BL. Then whatever the result in AL will be the gray equivalent of given binary number, that you have to store. Move SI comma 6000H, move AL comma contents of SI. So this original number AL I have taken into BL, or otherwise you can directly take this AL contents and then you can rotate this by 1 bit position. Okay. So this is the program for conversion of 8-bit binary number into gray number. So I will discuss one more program on subroutines. After that we will go to the next topic, program on subroutine. Simply this program will multiply one 8-bit number stored in some location with another 16-bit number. This is data segment, same address, say 50,000H, and let us assume that in 55,000H one 16-bit number is stored. $50,000, $55,001, and then 55,002 the second 8-bit number is stored. You multiply these two and you store the result. You store the result in some location stored in 4 consecutive locations. This is the end of the segment. some 56000H, 56001H, 56002H, 56003H. So store the result. Okay. Store the MSB of 16 bit here. So starting from LSB to MSB. Okay. So these are the requirements. But for this you can do it without subroutine also. So you do everything here in the main program, and the multiplication you write a subroutine separately. Okay. You write out the subroutine for the multiplication. Okay. So I am writing first main program. So in the main program you do the initialization and storing the result, but the actual computation of the multiplication you just perform in a subroutine. Okay. So move, I will come to some here, I will store something, move AX comma 5000 H, move DS comma AX. Okay. Then first 16 bit number is present in with location of offset of 5000. You store that offset into SI, because here both are same. I am taking AX content itself in SI. Then move AX comma contents of SI, so that AX will contain a 16 bit number. So they are both are signed numbers. Okay. Now 8 bit number is there in next location. So you have to take this onto some other register, say BL or CL, it is up to you, whatever it may be. CL comma contents of SI plus 2. SI was 5000, SI plus 2 is 55002, where the 8 bit signed number is present. This I am taking in CL. CL we have 8 bit number. This has to be multiplied, but in the subroutine. I do not want to multiply here, so I want to multiply in the subroutine. Okay. So for that, because this 16 bit by 16 bit you can multiply, or I mean 8 bit by 8 bit. Once 16 bit by 1 by 8 bit multiplication, there is no direct instruction in the 8086. So you have to do the sign extension of this CL. Okay. So for that we can store this, we can reverse it in fact. This I will store in CX, otherwise instead of AX I will store in CX, because for the sign extension I want this has to be stored in AL. So this I will store in CX. In CX I am storing 16 bit number, and this I am storing in AL. AL I am storing 8 bit number. Then I am calling multiplication subroutine, call multiplication subroutine. Okay. So I will write the multiplication subroutine somewhere. So before writing this subroutine, so I will discuss what is required at the main program. So whenever you want to call a subroutine, is you have to initialize the stack segment and stack register. Okay. So here we have, this is data segment. Similarly you have to define stack segment also. This is stack segment. So whenever you want to use these subroutines, we have to define the stack segment also. Let the starting address of start segment is some, say F0000H. So ending address will be 64 kilobytes, all Fs. This is in fact the last 64 kilobytes of the entire 1 megabyte of the memory. Okay. So in this we have to define the stack pointer till which point the stack is full. I will assume that up to here say stack is full. So if this is F D 0 0 some 2. So up to this stack is full. So we have some data 32, 45, 39, 45. Okay. So this stack pointer always holds the address of the stack top, which is the offset, and this is next available location. So this will be stored in stack pointer. So with this assumption, what you have to do is, so you have to initialize the stack segment register with F000, the upper 16 bit of the starting of that particular segment. So for that again the same thing. So move AX comma, the starting address is F000, then move on to stack segment register comma AX, because you cannot take directly any address onto segment registers. Then you have to initialize the stack pointer with FD00. Stack pointer you can take the direct address. Move stack pointer with, for this assumption, FD00H. Then we can write the call instruction, because so in the call instructions automatically what happens is the instruction pointer contents will be pushed onto stack. For that you have to define the stack pointer and stack segment. Now what will be the instruction set multiplication subroutine? This is mul subroutine, say. From here to here, mul subroutine. So what are the instructions required at the mul subroutine? Because here in the main program we are using AX register and CX register. So we have to first push these registers. Because here also you have to use the same registers for the operation of this subroutine also. Okay. Then what is to be done here? Just only simply multiplication. So the contents of CX has to be multiplied with contents of AL. But the problem is here AL is having only 8 bit. So we can perform only 16 bit by 16 bit multiplication or 8 bit by 8 bit multiplication. But these two sizes are not same. So in order to convert this 8 bit AL contents into 16 bit, we will write CBW. So that in AL what will be there? The sign bit will be copied. So then AX will be having this 16 bit number, which is sign extension of 8 bit number, sign extended 16 bit number. Now we can perform the multiplication, IMUL. So one of this operand has to be taken in AX in case of 16 bit by 16 bit multiplication. In 8 bit by 8 bit multiplication, one of the operand has to be taken into AL. So here I have taken one of the operand in AX, another operand in CX. Simply how to write IMUL CX, so that the result is stored in DX and AX. Okay, that you have to store in 56,000 to 56,003. So now the operation is over only. So this is just to explain the subroutine concept. I have written this program, but the task in the subroutine is only just simply multiplication. Okay. Then before returning to the main program, so whatever the contents it has been pushed, now it will be popped in a reverse manner. Pop CX, because the stack is last in first out register. So pop AX, then return. These are the set of the instructions which basically multiplies. So before the multiplication, because we want only either 16 bit multiplication or 8 bit multiplication, you have to make both the operands same size. So here one operand was 8 bit, so we converted into 16 bit by using CBW, then we return back. So here only this in the main program, what is left now? Only storing the result. Okay. So here I am storing the result, move SI comma 6000 because I want to store the result in the memory location with the offset starting from 6000 to 6003. So, here the result will be there after I mul Cx in dx and ax. So, I am going to store the LSB result in 56,000 move Si comma ax move Si plus 2 comma dx. Alt. So, the 16-bit result will be stored in these 4 locations 56,000 to 56,003. This is about simple a multiplication of 8-bit number by 16-bit number, but using the subroutine concept. Okay. So, these are some programs that I have discussed in the last 2 classes. Okay. Now, I will discuss some more programs while discussing about the I/O interfacing. If you want to interface input device such as keyboards, 7-segment displays, we need some programming also there. Okay. We need some hardware as well as some programming. Okay. So, there we will discuss some more programs. Now, I will stop the programs here and I will go to the next topic, which is the third part of this course. So, this course is basically the architecture, instruction set and the programming. We can call as programming itself. For programs we require the instructions, okay. And the third part is interfacing. As I have told, there are this course we have basically 3 modules. Architectural details, including pin diagrams, this we have discussed. Then we have discussed the programming. Programming in sense we require the instruction set. The third part is interfacing. So, we have in the interfacing we need some hardware as well as in some cases to interface some I/O devices we require some programming also. Okay. So, we will discuss some applications also here. So, the first interfacing is, as I have told, the microcomputer will be having microprocessor, then I/O memory. This is microcontroller. This is the block diagram of a microcomputer. So, in that microprocessor will act as CPU and then memory and I/O. So, how to connect the memory and I/O to the microprocessor. Without this memory and I/O interfacing, the microprocessor will not perform any operation. Okay. So, microprocessor has to be connected to the memory as well as I/O. Okay. So, how to connect memory to the microprocessor, how to connect I/Os to the microprocessor. This is what is called interfacing. How to interface the memory to the microprocessor, how to interface I/Os to the microprocessor. First, I will discuss the memory interfacing. Before going for the memory interfacing, I will review some details of the memory, because the memory is required here, memory details are required to interface the memory to the microprocessor. So, memory, basically there are 2 types of the memories. Read only memory, random access memory. Again, in this read only memory there are different types like PROM. So, we have here again in the ROM we have programmable read only memory, erasable programmable read only memory, electrically erasable E-square PROM. Similarly, in RAM also we have static and dynamic. So, before going for the actual this what is ROM and what is RAM, so how does the memory will be represented? So, normally we will call the memory as some 32 kilobytes. What is the meaning of this 32 kilobytes? Is, or simply if I take This is equivalent to, as I have told in the earlier classes, 1 kilo in microprocessor terminology is 1024 and 1 byte is 8 bits. So, the meaning of 32 kilobytes is equal to, this is 32 into 1024, 1024 into 32, this is equivalent to 32,768. So, this is 32,768 is the first one into 8. So, this represents the number of locations, number of memory locations, and this represents the number of bits in each location. This is the meaning of a memory. So, simply if I take a small memory like say 8 by 4 ROM, any memory, it can be either ROM or RAM, I will call as memory, 8 by 4 memory. What does it mean? So, it means we have 8 locations, one, 2, 3, 4, 5, 6, 7, 8, and each location is capable of storing 4 bits of information. Each bit can be 0 or 1. Okay. So, there are total 8 locations. If I number this one as 8 locations, to number the 8 locations, how many bits are required? So, this 8 you have to represent as a power of 2, 2 cube. So, 3 bits are required to address the each location. Okay. So, normally all the memories will be having the number of locations is a power of 2. Okay. So, here I will call this one as 000, 001, this we can call as the address. The address of the first location will be 000, then the second one is 001, 010, 011, 100, 101, 110 and 111. Okay. So, in case of read only memory, we can only read the data. So, at the time of manufacturing itself, some data will be stored into the ROM. Okay. So, whatever that may be, so the first block here is we have 3 address lines, but we have 8 locations. Okay. So, how to choose for each combination of these 3 lines? If I call in general this one as A2, A1, A0. So, we have 3 address lines A2, A1, A0. Total we have 8 combination. For each combination, one of the memory location is to be selected. Okay. This operation will be performed by using a digital circuit called decoder. So, basically the first block of any memory is a decoder. Okay. So, here if I want 8 by 4 memory, then we require 3 by 8 decoder. If I take the structure of this one, 8 by 4 memory, if I take say read only memory directly. So, the first block will be 3 to 8 decoder. So, with 3 inputs A2, A1, A0 and 8 outputs Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7. So, what are the Boolean expressions for these outputs which we have studied in digital logic? Basically, Y0 is if I use the positive logic, basically we are having Y0 bar, Y1 bar, because NAND gates are universal gates, normally we will use NAND gates. Otherwise, what is the expression for Y0 is complements of all the three, A2 bar, A1 bar, A0 bar. Okay. Basically the decoder block diagram will be, so if I take this A2, A1, A0, the truth table of the decoder, and output, this is inputs and outputs. Truth table represents relation between the inputs and outputs, y7, y6, y5, so on up to y4, y3, y2, y1, y0. So decoder is a combinational circuit with n inputs and 2 raised to the power of n output, maximum of 2 raised to the power of n outputs. In some cases they can be less than 2 raised to the power of n outputs also, like in case of BCD 7 segment display. BCD is 4 bits, 7 segment display is, as the name implies, 7 bits, so which is less than 2 raised to the power of 4. But in general the decoder will be having n inputs and a maximum of 2 raised to the power of n outputs. For each combination of the inputs, one of the output is selected. Okay. Here for 0, 0, 0, only y0 will be selected. For 0, 0, 1, only y1 is selected. Similarly, for 1, 1, 1, only y7 is selected. So if I want to write the Boolean expression for this one, y0 is 1 here. If I take this y0 column, so only one min term is there. So the relation is y0 is equal to A2 bar, A1 bar, A0 bar. And if I take the y1, A2 is 0, A1 is 0, A0 is 1. So this is basically y1 will be A2 bar, A1 bar, A0. Okay. Because all these details are required to interface the memory to the microprocessor. So inside this decoder we will be having 8 3 input AND gates. Okay. And sometimes we can have some enable signal also. So suppose if I want to disable this entire decoder itself, here there is no option, at any time only one of the output is selected. Okay. So for that what I will do is, so I will make one signal such that output will be 0, none of the output will be selected, that you can call as enable signal. Okay. That I will discuss later. So this is about basic 3 by 8 decoder. Now in order to store 4 bits, what you have to do is, so we will be having so many OR gates. In case of ROM, the first 8 represents, this is the output of the decoder. Accordingly you can find out the number of input. The first block is a decoder and second block is an array of OR gates. So the number of OR gates will be equal to the number of bits that is to be stored in each location. Here we have 8 by 4 means 4 OR gates will be there. So in each location I want 4 data lines. I will call this one as D3, D2, D1, D0. These are address lines, these are data lines. So any memory will have some address lines and some data lines. Similarly microprocessor also having some address line, data lines. So in order to interface we have to basically connect the address lines and data lines together, and we have to select that particular memory using some chip select signal. Data lines are data bus. Now whatever the number of outputs of the decoder, so that we have to give as input for this all the OR gates. So all the OR gates are 8 input OR gates. Even though I have represented with single line, this is in fact all the 8 inputs are connected to this particular line. Now depends upon the data that is to be stored in each location. So here all this will be connected through the fuses. Here we will be having fuses. At each intersection you have fuses. If fuse is intact, then that particular line will be connected to the input of OR gate. If fuse is blown, then there will be no connection. So, fuse can be either intact or blown. So, depends upon the data that is to be stored here, we will either intact the fuse or we will blown the fuse. Okay. So, how to store the data in each location, that I will discuss in the next class. Thank you.